Welcome to this audio presentation where we explore Sir Oliver Lodge's work on the ether and fundamental concepts of electricity. While the ether has fallen out of favor in modern physics, this historical perspective offers fascinating insights into how it was once regarded as central to understanding the universe. Now, this text is from the introduction and first chapter of Modern Views of Electricity by Sir Oliver Lodge. This work bridges the classical and emerging ideas of electricity and magnetism from the late 19th and early 20th centuries. Let's dive in.
Introduction.
The ether. The most interesting and important portion of physics at the present day is that constantly growing portion which is concerned with the properties and function of the universal connecting medium, the ether. All the phenomena of light, of electricity, and of magnetism, as well as of what is spoken of as radiant heat, are intimately connected with, and indeed wholly dependent on, that medium. It is through these agencies that we have gradually become aware of its existence and able in some degree to investigate it. Probably gravitation, cohesion, and chemical affinity are no less closely associated with the ether, and it is becoming doubtful whether matter itself could exist without it. The eye may be called an ethereal sense organ, just as the ear is an aerial one. Both are adapted to appreciate ripples, the one large ripples or waves in air, the other minute ripples or quivers in ether. The appreciation of those electrical ripples or quiverings, insignificant though they are from many points of view, is intensely important to us. Without the power of apprehending the ripples thrown off and reflected from and scattered by the several objects in our neighborhood, we should be both blind and deaf. It is only by inference from the way they deal with and disperse the ethereal quiverings that we become aware of odorless objects beyond the range of our touch. We are said to see them. In a room where the ether is quiescent, we can see nothing. But if by any means, as by lighting a candle, we throw it into vibration, the vibration returns to our eyes from all the objects in the room. Thereby, through habit and experience, we gain such quick intuitive information concerning those objects that we are not conscious of the means of information and express our perception as if it were direct and immediate by saying that we see the objects themselves. That is, in fact, what we mean by seeing. We do not see the waves, we see the obstacles. But it is entirely by means of the ethereal waves that the existence and nature of the objects are inferred. The extraordinary precision and rapidity of this mode of inference is perfectly marvelous and could never have been believed if it had only theoretically been explained. Before beginning a book on electricity, where we are to come into contact with other properties and functions of this most interesting and omnipresent medium, it is as well to exercise our imagination concerning it and try to realize the vitally important part it plays throughout the universe. Probably we are far from knowing all its functions as yet, but knowing many of them, we suspect more. The reader is recommended to turn to a couple of lectures on the subject, which he will find printed on pages 359 and 450 further on, and read those at intervals before and during his perusal of the rest of this book, for they will serve as a useful introduction. The book as a whole, beginning with a survey of well-known and elementary phenomena, leads up to the generalizations shadowed forth in Chapter 17 and Lectures 4 and 6, which attempt to indicate how the idea of ether and the idea of electrons can be combined so as to supplement and illuminate each other. The hypothesis ultimately suggested is that excessively minute portions of ether have, by some unknown means, been dissociated here and there into electric charges, and that these immensely numerous mobile specks of electrified ether, through the forces they exert and the disturbances they originate, constitute the substratum of what appeals to our senses as matter. Chapter 1, saying that the whole subject of electricity is divisible, for purposes of classification, into four great branches. First, electricity at rest, or static electricity. This branch studies all the phenomena belonging to stresses and strains in insulating or dielectric media, brought about by the neighborhood of electric charges or electrified bodies at rest, immersed therein, together with the modes of exciting such electric charges and the laws of their interaction. Second, electricity in locomotion or current electricity. This branch discusses all the phenomena set up in metallic conductors, in chemical compounds, and in dielectric media by the passage of electricity through them, together with the modes of setting electricity in continuous motion and the laws of its flow. Third, electricity in rotation or magnetism. Herein are discussed the phenomena belonging to electricity in whirling or vortex motion, the modes of exciting such whirls, the stresses and strains produced by them, and the laws of their interaction. Let me know if you'd like. 4. Electricity in vibration or radiation, wherein are discussed the propagation of periodic or undulatory disturbances through various kinds of media, the laws regulating wave velocity, wavelength, reflection, interference, dispersion, polarization, and a multitude of phenomena studied for a long time under the heading light. Although this last is the most abstruse and difficult portion of electrical science, a certain fraction of it has been known to us longer than any other branch, and has been studied under special advantages because of our happening to possess a special sense organ for its appreciation. Now, in order to be able to survey these four great and comprehensive groups in moderate compass, it will be necessary for me to assume acquaintance with the elementary facts and proceed at once to their elucidation. The views concerning electrification, which I shall try to explain, are in some sense a development of those originally propounded by that remarkable man, Benjamin Franklin. The accurate and acute experimenting of Cavendish laid the foundation for the modern theory of electricity, but as he worked for himself rather than for the race, and as, moreover, he was in this matter far in advance of his time, Faraday had to go over the same ground again, with extensions and additions peculiar to himself, and corresponding to the greater field of information at his disposal 3/4 of a century later. Both these men, and especially Faraday, so lived among phenomena that they yielded up their hidden secrets in a way unintelligible to ordinary workers. But while these men themselves arrived at truth by processes that savor of intuition, they were unable always to express themselves intelligibly to their contemporaries, or to make the inner meaning of their facts and speculations understood. Then comes Maxwell, with his keen penetration and great grasp of thought, combined with mathematical subtlety and power of expression. He assimilates the facts, sympathizes with the philosophic but untutored modes of expression invented by Faraday, links the theorems of Green and Stokes and Thomson to the facts of Faraday, and from the union rears the young modern science of electricity, whose infancy a quarter of a century ago was so vigorous and so promising that we all looked forward to the near future in eager hope and expectation of some greater and still more magnificent generalization. Everyone knows that there have been fluid or material theories of electricity for the past century. All know, moreover, that there has been a reaction against them. There was even a tendency at one time to deny the material nature of electricity and assert its position as a form of energy. This was doubtless due to an analogical and natural, though unjustifiable, feeling that just as sound and heat and light had shown themselves to be forms of energy, so in due time would electricity also. If such were the expectation, it has not been justified by the event. Electricity may possibly be a form of matter. It is not a form of energy. It is quite true that electricity under pressure or in motion represents energy, but the same thing is true of water or air, and we do not therefore deny them to be forms of matter. Understand the sense in which I use the word electricity. Electrification is a result of work done and is most certainly a form of energy. It can be created and destroyed by an act of work. But electricity, none is ever created or destroyed. It is simply moved and strained like matter. No one ever exhibited a trace of positive electricity without there being somewhere, connected with it by lines of force, an equal quantity of negative. The simplest proof of this statement consists in making experiments inside a closed conducting insulated room or shell. It may be the size of a living room or the size of a beer tankard, whichever is most convenient. All known electrical experiments being performed inside such a room, bodies electrified strongly, moved about, sparks taken, and so forth, a sensitive electroscope connected to the room shall not show the slightest permanent effect. In other words, the room will not become in the slightest degree charged. I say no permanent effect, because it is just possible that small transitory effects may occur during the rapid rearrangement of internal charges. I believe that I have shown that even transitory effects are not really possible, but whether they are or not, they have nothing to do with our present argument. All the electrifications that have been going on will not have resulted in the creation of the minutest quantity of electricity. The only way to charge the room is to convey a charge to it from some other body outside. This is the first great law, expressible in a variety of ways, as, for instance, by saying that the total algebraic production of electricity is always zero, that you cannot produce positive electrification without an equal quantity of negative also, that what one body gains of electricity, some other body must lose. Now, whenever we perceive that a thing is produced in precisely equal and opposite amounts, so that what one body gains another loses, it is convenient and most simple to consider the thing not as generated in the one body and destroyed in the other, but as simply transferred. Electricity in this respect behaves just like a substance. This is what Franklin perceived. The second great law is that electricity always, under all circumstances, flows in a closed circuit, the same quantity crossing every section of that circuit, so that it is not possible to exhaust it from one region of space and condense it in another. Another way of expressing this fact is to say that no charge resides in the interior of a hollow conductor, but that every trace of charge is on the outer surface and penetrates to no appreciable depth. Another is to say that total induced charge is always equal and opposite to the inducing charge. The second law can also be illustrated by the insulated room or conducting cavity already mentioned. Having found that internal electrification produces no effect on an outside electroscope connected to the walls, proceed to pass a charge into the cavity through a temporarily opened window or lid. Instantly, the chamber has become charged by a definite amount, namely by the precise amount which has then been introduced into its cavity. The charge need not be in any way communicated to the chamber. All that is necessary is that it shall be wholly inside. Moving the charge about, or letting it spark to the walls of the chamber, makes not the slightest difference to the electroscope outside. It may be watched through a microscope at the instant the spark occurs, and it will not show the slightest twinkle, although it is connected to the enclosure by a metallic wire or rod. Both these experiments of the hollow chamber were made by Faraday, and the latter is well known and often quoted as his ice pail experiment, because he happened to use an ice pail sometimes as his insulated chamber. In many modern experiments, this principle is utilized, and the device is spoken of as Faraday's hollow or collecting vessel. Another mode of illustrating the same series of facts is afforded by an insulated parrot cage, with an electroscope inside it connected by a wire to the bars of the cage. The cage may now be charged strongly. Its potential may be changed from 1 million volts positive to 1 million volts negative. Sparks of any length may be taken from it, but provided the meshes are close enough for it to be regarded as a really closed vessel, the electroscope inside is wholly unaffected. In making this experiment, the electroscope must be connected with the bars of the cage, for if it is detached, it can be affected by charged air blown through the meshes. Directly a charge gets inside the cage, it can affect the electroscope easily enough unless there is good wall connection, which completely protects it. The open work of a cage is objectionable on this account, as it allows the permeation of electrified air, just as it might allow an electrified pith ball to be thrown in. Making the meshes close is no guarantee against this source of disturbance. I have blown electrified air from a point through very fine earth-connected copper gauze and affected strongly an electroscope on the other side. No doubt a solid metal-walled room is secure against this cause of disturbance, but then it is difficult to see the electroscope. Faraday, however, constructed a room for the purpose, big enough to get into himself, and thus performed the experiment quite satisfactorily. But perhaps the most rigorous mode of examining the precise truth of the property of electricity, which lies at the bottom of all these experiments, is that adopted in the famous Cavendish experiment, sometimes referred to in French books by the name of Biot. This consists of strongly charging an insulated sphere provided with a couple of hemispherical caps, which can afterward be taken off mechanically, and connecting a delicate electroscope immediately afterward to the disclosed ball. Not the faintest trace of charge is found upon it. This experiment was repeated by Clerk Maxwell and Dr. Donald McAllister in the Cavendish Laboratory, Cambridge, using a Thomson quadrant electrometer and all modern appliances, with absolutely negative results. This series of experiments is most vital and gives us fundamental information regarding electricity. Let us consider how we can best express their teaching. When we thus find that it is impossible to charge a body absolutely with electricity, that though you can move it from place to place, it always and instantly refills the body from which you take it, so that no portion of space can be more or less filled with it than it already is. When it is impossible, by any rise of potential, to squeeze a trace of electricity into the interior of a cavity, and when introducing a charge causes a precisely equal quantity to pass through the walls to the outside, it is natural to express the phenomenon by saying that electricity behaves like a perfectly incompressible substance or fluid, of which all space is completely full. That is to say, it behaves like a perfect and all-permeating liquid. Imagine now that we live immersed in an infinite ocean of incompressible and inexpansible, all-permeating perfect liquid, as fish live in the sea. How can we become cognizant of its existence? Not very easily. Not by its weight, for instance, since we cannot remove it from any portion of space to try whether it has weight. We can weigh air, truly, but only because we can compress it and rarefy it. But if air had been incompressible and inexpansible, if it had been a vacuumless perfect liquid, pumps would have been useless for this purpose, and we would necessarily remain completely ignorant of the weight and pressure of the atmosphere. How, then, could we become cognizant of its existence? There are four ways. 1. By pumping it out of one elastic bag into another, not out of one bucket into another. If you lived at the bottom of the sea, you would never think about filling or emptying buckets. The idea would be absurd. But you could fill or empty elastic bags and notice the strain phenomena exhibited by the bags, such as their tendency to burst when overfilled. Water or air may be pumped out of one elastic bag into another, and the analogy with an electrical machine charging two conductors oppositely, pumping electricity from one into the other, may be perceived. 2. By winds or currents. This involves watching the effect of moving masses of the fluid as it flows along pipes or through spongy bodies, and observing the effects of its inertia and momentum. A hanging vane arranged in a tube, deflected by a stream of water, may be roughly likened to a galvanometer. Also, the effect of suddenly stopping a stream of water, as in a water ram, is somewhat analogous to self-induction. 3. By making vortices and whirls in the fluid. This entails observing the mutual action of these vortices, such as their attractions and repulsions. Whirlwinds, sandstorms, waterspouts, cyclones, and whirlpools have some analogies with an electromagnet. 4. By setting up undulations in the medium. These phenomena in ordinary media excite in us, through our ears, the sensation called sound. In all these ways, we have become acquainted with electricity, and in no others that I am aware of. They correspond to the four great divisions of the subject I mentioned earlier. Differences between electricity and an ordinary fluid. There are, however, differences. At first sight, important differences between the behavior of electricity and that of an ordinary incompressible fluid. The chief difference emerges in the fourth category, concerning wave motion. In an incompressible fluid, the velocity and length of waves would both be infinite, and none of the phenomena connected with the gradual propagation of waves through it could exist. Such a medium would, therefore, be incapable of sound vibrations in any ordinary sense. On the other hand, it is quite certain that the disturbances involved in light radiation take place at right angles to the direction of propagation. They are transverse disturbances. Such disturbances cannot be transmitted by a body with the simple properties of an ordinary fluid. They can only be transmitted by a medium possessing something akin to the rigidity of a solid. We must admit that the ether, though fluid in the sense of enabling masses to move freely through it, has a certain amount of rigidity, at least for enormously rapid and minute oscillatory disturbances. How can a fluid possess rigidity? Is there any way to confer rigidity on a fluid without solidifying it? It can be shown that although a fluid at rest has no quasi-solid properties, a fluid in motion acquires them. Drive water rapidly through a flexible tangle of India rubber pipes with both ends fixed, and it instantly becomes semi-rigid. Utilizing this fact, imagine every particle of a massive fluid in a state of violent motion, not locomotion, but motion in minute closed curves, known as vortex motion. In this state, the fluid becomes rigid or quasi-solid, acquiring the property of transmitting transverse waves. The gross analogy of a jelly is occasionally useful. A jelly is composed almost entirely of fluid and yet is rigid. Its rigidity arises from the elastic skin surrounding each particle of water. Distend a thin India rubber balloon with water, place it on a plate, and it looks and behaves much like a jelly until collapsed by a needle prick. The effect of an elastic skin which rigidifies stagnant water can be more perfectly imitated by setting the water into a state of fine-grained vortex motion. All kinds of elasticity are explained, as Lord Kelvin has shown us, by simple motion. Not a simple fluid, but a fluid in a violent state of minute spin, a vortex sponge, as it has been called, is what the ether is likely to turn out to be. As this conception is presently difficult, we can vaguely say that the ether contains electricity as a jelly contains water. The rigidity concerned in its transverse vibrations belongs not to the water in the jelly, but to the mode in which it is entangled within its meshes.